Okay, everyone. Today we're delighted to have Frank Zhang joining us from Princeton. He's a graduate student there, advised by Zhang Krishnan, who also visited us last year. And according to Frank, his ultimate goal of his PhD study is to become a quantum magician. And even though he's only at his third year of pursuing his magician path, career path, he's already doing some magical work. And today, let's hear him talking about one of these.
Oh yeah, thanks for the very wonderful introduction. It's a great pleasure to be here and try to preach some of my magic. And I'm going to talk about not the Harry Potter kind of magic, but magic as a kind of quantum resource. I'll explain what it is later on. And I will tell you how people used to believe that magic gives you quantum advantage, but we challenge that belief by showing that the distribution of magic where they locate in the quantum circuit could actually greatly affect the computational power of a quantum circuit. So without further ado, and this is George, what was you showing over here? No, yeah. Okay, so let me start with the story. Once in a while, you see on the news that some major industry academia collaborations, they published some big science Nature paper where they did some very complicated quantum experiments and they claim quantum advantage, like you need like 1 septillion year to simulate the same experiment on classical computer. And yeah, there's different branding, supremacy, utility, advantage, whatever you want. But in a few months, you'll see a bunch of papers saying, okay, I can simulate the same experiments on a personal laptop over here, and I can do that in 2 minutes. Yeah, so that's quite disturbing to me. And at least one reason why this happens all the time, not all the reason, but one major reason is that all the current quantum computers, they are quite noisy. So they're at the noise rate of like 0.1% to 1%. That's like for every 1 gate in 100 gate, there's 1 gate that's faulty, and that's not good. And these classical algorithms, some of them, they exploit the fact that your quantum computer has noise to spoof their quantum advantage. Okay, so that's bad, but we know a path to circumvent the noise, which is quantum error correction. So the idea of quantum error correction is that you trade your number of qubits with noise. So you have like 4 physical qubits, maybe even more. They are pretty noisy and they're heating up. Now, what you do is you do some operation to entangle the physical qubit such that in the big qubit space, there's a 2-dimensional subspace that hides a logical qubit. And this highly entangled 2-dimensional subspace, you see less noise. So that's what it means to do error correction. You use more resource to trade for noise. And let me point out that 10 years ago or 20 years ago, this is a theory's fantasy, but now it's actually happening. We do have at least one experiment where people are using something called surface code. Doesn't matter where it is. If you don't know where it is, that's fine. But as they use more qubits to build a bigger quantum error correcting code, they see that the error rate in this logical subspace decreases exponentially. So every time, let's say you add, very roughly, you add 10 qubits, you can cut down your noise by 2-fold. So what that means is you can just keep adding qubits, and as you add more qubits, your noise decreases exponentially. And that's great, because exponential is really fast. But there's a caveat. So we know almost 10 years ago that if you just have one quantum error correcting code, you cannot have a universal and transversal gate set. And let me explain terminology a little bit. Universal means you can generate any unitary you want, so you can do all the operation you want for quantum mechanics. Transversal means you don't spread out noise. So this is basically a criteria for quantum error correcting code to work. If you spread out noise, the code will break down. So in human language, this means that you cannot simultaneously do all the operations you want for quantum computing and not screwing up your quantum error correcting code and protecting your qubit from noise. So that's really bad. And for practical purposes, almost all the gates that are transversals, so the good gates, they're all Clifford gates. it's a gate set generated by Hadamard, C0, and S gate, which is a 90-degree rotation along the z-axis on a Bloch sphere. It doesn't really matter what they are, but they have a very special symmetry. So these operators, these unitaries, if you evolve any Pauli operators with these unitaries under the Heisenberg evolution, you turn that into another Pauli operator. So for example, if I evolve xz with C0, so it's like u, xz, u dagger, you turn that into a different Pauli operator, yy. And because of the symmetry, we actually know that Clifford circuits can be simulated classically very efficiently. And the trick's the following. So you start with, let's say you start with a zero state as your initial quantum state. And we know that zero state, you can think about it as a ground state of a Hamiltonian, that's Z1 plus Z2. So you want your state to be the +1 eigenstate of Z1 and the +1 eigenstate of Z2. So I'm going to call this operator Z1, Z2 stabilizers as they stabilize the state. You know the stabilizer, you look at the eigensubspace, you get the state. And we have two generators, Z1 and Z2. I can form a group with it. It's a group with 4 elements, and this state 0, 0 is the eigenstate of every element in the stabilizer group. And in this way, I can write down my state or the density matrix literally as a uniform sum of the stabilizer group, which is something very tractable because all you need to know is the generator. If you know a generator, you know a group. And now to evolve this Hamiltonian, evolve this state with the unitary, you just evolve this operator. You evolve this operator by conjugating with the Clifford unitary, but you know that if you conjugate with Clifford unitary, it's still a Pauli operator. So that's why it's classically simulable. Instead of like writing down the state as a state vector representation, 2 to the n entries, instead you just keep track of these generators and see how they evolve under Clifford unitary. And that's just a permutation action. You look at how Pauli goes to another Pauli and so on. So that's very easy. Okay, so we know that quantum error correcting code gives you a limited gate set, which is Clifford, and they are classically simulable. So why even bother with quantum error correction? So it turns out to really get power in quantum computing, you just need one more gate. You need a gate that's not a Clifford gate. And here's the point where I define magic. Unfortunately, this is not a very good terminology. Clifford, magic just means a gate that's not Clifford. And one standard example is a T-gate. T-gate is a Z rotation that's 45 degrees. If it's a 90-degree rotation, that's in Clifford. Now I cut in half, it's 45-degree rotation. So T-gate, if you add just T-gate to the Clifford gate, it forms a universal gate set, which means you can approximate any unitary using a combination of Clifford gates and T-gate. And now T-gate is not a native gate set. It's not a transversal gate to a quantum error correcting code. So you need something else to be able to apply this gate. And there's a protocol for it. It's more complicated. You have to do something like a teleportation. So you have to start with a resource state called magic state, where the state somehow encodes a 45-degree angle information in the phase. And you somehow you teleport this phase into your quantum error correcting code. I'm not going to talk about detail, but it's more costly. And in particular, for this gate to operate this gate with high fidelity, you need to prepare this resource state with high fidelity. And to do that, you have to do something called a magic state distillation. That's basically a process where you use some really specialized quantum error correcting code to turn like 5 copies of noisy magic state into one better copy of noiseless, less noisy magic state. This is usually, not always, but usually considered the most expensive step in doing fault-tolerant quantum computing. So we really are, at least at this stage, I still believe that we're still limited by the number of magic resource we have. So that's why we call it resource. It's something scarce. You don't have that, like at least in the near term, you don't have a lot of magic gates. Okay. And let's talk about now, after you add the magic gate, how does the classical simulability change? I'm just showing a table of all the, like most of the classical algorithms simulating Clifford plus T circuits. Just look at their runtime. M is the number of T gates in your circuit. They always grow exponentially. So as you add more T gates, the runtime grows exponentially, and the major overhead, the major effort here is to cut down the exponents, like let's say from 0.48 to 0.23, maybe even lower. We don't know. Yeah, but this is fundamental, and I'll show you that this is actually no. There's some special structure we can exploit in this kind of circuit, and if you have this kind of structure, you can get a very efficient classical algorithm for simulating quantum circuits with like a lot of T gates, order n T gates. Okay, and the insight here is that magic gates are the gates that generate superposition in the Pauli basis. So I just told you that Clifford gates, they map Pauli operator to Pauli operator. So it's like a permutation. I don't generate like a coherent sum of a different Pauli operator. On the other hand, magic gates, like T gate, it generates superposition. So I evolve X with T dagger. I generate square root 2 of X plus Y. So it's a sum. Question? Oh yeah, sorry, that's why Y. Yeah, that's why Y. Sorry, that's a typo. I think I correct one of them, but not the other one. Yeah, good catch. Thank you. But back to sorry, you generate superposition using magic in the Pauli basis. As an analogy, you can think about how Hadamard gate, when you act on 0, it generates 0 plus 1. So it's a superposition. Magic is the same, but now you're generating the superposition in a different basis, in a Pauli basis. And we know that quantum computer is not classical simulable because of interference. Interference is a process where you have a lot of paths, you have some sum of paths, and you add some phase to the paths and you sum it up. And something will add up constructively, something add up destructively. And let me show you a circuit with no interference at all. And this is a circuit, I call it Hadamard depth 1. So you start with 0 state, you add 1 layer Hadamard. So at this point, your quantum state is a uniform superposition of all bit string. It's super simple, you know exactly where it is. And now I'm gonna do a lot of complicated gates. But look at these gates. T gate is a phase gate, S gate is like a permutation. You swap 0 with 1, 1 with 0, Y and Z are very similar. And these are all basically, they add phase or they permute your computational basis. In the end, you get a state like this. It's this type of E to the I phi x. I don't know why someone type typos. It's a phase. So for each amplitude, for each computational basis, you're now equipped with a phase. But now if you just measure the state in the computational basis, you get a uniform distribution. Why? Because these all have the same amplitude. You change the phase, but you haven't interfered them yet. You have to do interference to sum up some of the paths, and you have some destructive interference in some other paths. And after doing that, you get some distribution in your classical measurement outcome, and that gives you power. So yeah, so what you do then is you add another layer Hadamard. Here you get some complicated phase. Again, this is E to the I phi x. Sorry, it's not W. And after Hadamard, you start to sum up paths. That's where you do interference, and that's where your amplitude becomes complicated. Some amplitude becomes bigger, some amplitude becomes smaller. And in fact, we know that this kind of circuit already gives you some power. For example, one version of Shor's algorithm where you factor integers looks exactly like this. So this is already enough to create quantum advantage, a useful quantum advantage, and we believe that there cannot be classically simulated. So as a physics analogy, we should really think about the circuit as a many-body version of interferometry. So the Hadamard gates are a beam splitter. You're sending a laser, the Hadamard splits into a different path, and then you add phase elements to delay some of the paths, and then you have to use a second beam splitter to merge the paths again, and then you see maybe this detector sees a larger amplitude, this guy sees a small amplitude. That's basically the physics analogy. Okay. And we'll do the same story in the polar basis now. So what we're gonna do is we'll consider following kind of circuit where I start with 0. I evolve with some Clifford gates, some generic Clifford gates. I don't put any restrictions. And then I have 1 layer magic gate. So it's like I have only 1 layer of beam splitter. I don't limit the number of beam splitters in my circuit, but I require that they are all in one layer for the intuition that you don't create interference. And then I can do some other Clifford. And for technical reason, I'm going to restrict to magic gates that are diagonal, so they are phase gates. But practically all the relevant magic gates are diagonal, so it's not much of a constraint. And I'm going to consider 3 different kind of tests. Like, what does it mean to classically simulate a circuit? I have to be a little bit more precise about it. You can compute amplitude, so literally evolve a circuit with some unitary, and then look at the amplitude on some, let's say, computational basis. You can compute like observable, and in particular, you want to compute polyobservable. And note that I'm here squashing out this second layer Clifford by just identifying some other this U dagger PU with some other poly. So I'm just removing that and not restricting my poly operator. This is not super important. And lastly, the quantum computer is a sampling machine, so I should also consider a task of sampling this state in the computational basis. Okay, I think people looks pretty happy, so I'll keep going on. I'll first present the result, and I'll explain why it happens. So first thing, if I restrict the magic layer to be T gate, so the gate that I just showed you, turns out computing amplitude surprisingly is already hard. I'll explain what it means to be gap P complete. But basically, if you can compute amplitude in one layer T gates, you can do any path integral. And similarly, sampling is also hard in the circuit already, modulo some complexity theoretic conjectures. But computing polyobservable is easy. We have a very efficient classical algorithm for doing that.
Mm-hmm. So this P layer, or sorry, the magic layer can be anywhere, or does it need to be sandwiched between some non-identity Cliffords?
Yeah, so we require that. So this Clifford and that Clifford can be anything. So for example, this can be identity. This doesn't have to be identity. So this can, I guess you're saying this can be in the first layer, can be in the last layer, can be anything in between. But it seems that there's only one layer. There's only one layer where you have T gates or magic gates. Okay. Everyone all cool? Yeah, by the way, feel free to interrupt me.
So there is a way to show that this representation is a good one in a sense that if you have 2 layers of T gates between the Cliffords, you cannot adjust the Cliffords to make the 2 layers to 1 layer.
Okay, that's a very good question. That is not true. There are actually instances where you can write down 2 layers, in fact, arbitrary layers, and then you can push them all into 1 layer. I will show later on.
Okay, that one is not a good really classification because it's not. It's a sort of if it were if we would be able to split to the equivalence classes in the sense, right? So then it would be nice, like 1 layer, 2 layers, and so on, and they are not intersecting.
Yes.
Now we can go between them by adjusting the Cliffords.
Yeah. Let me put it this way. Yeah. So you're definitely right in the sense that just by looking at one particular circuit, look at this guy maybe have depth 2, doesn't mean it cannot be put into depth 1. What I'm saying here is that if you have a representation that's already in depth 1, then you can exploit the structure to do classical simulation. But I guess it's not really in the sense like a classification or phase matter kind of thing. It's not a robust feature. And in fact, we do know ways to reduce the magic depths, which I'll talk about later on. That's actually beneficial for the purpose of classical simulation because you have less magic depths. There's more structure you can exploit to do classical simulation. And I'll explain later on. Yeah, but good question. Okay. Going back to polyobservable, I just told you that polyobservable is classically very easy. It's order n cube classical simulation time. But this is really because of a special feature in T-gate. T-gate has some special symmetry. Now, once you break that symmetry, for example, I take square of T, so it's like 22.5 degree rotation rather than 45 degree rotation, I can show that computing polyobservable becomes hard again. Similarly, if I just add 1 more layer T-gate, computing polyobservable becomes hard. So this is tight. And this is the hardest you can ever expect. But the previous result, they hold all the hardness result, they are about computing that operator either exactly, or you allow a small multiplicative error. So multiplicative error means you can be 10% off. So if your actual ground truth is like very, very small, then by being 10% off, your error bar has to be small as well. And that's not a realistic error bar. In real life, quantum computer is a sampling machine, and in polynomial time, you can only achieve inverse polynomial additive error. So your error bar is absolute, doesn't care about what's your ground truth. And in this regime, we can show that if you allow like inverse polynomial additive error, then you can actually compute amplitude and poly-observable efficiently. A question?
Because when you say T-depth2, you have a more general
yes.
circuit.
Yes.
So why it's harder? I could imagine that I have more freedom.
Yeah, so it's a bigger class. So naturally, T-depth2 includes T-depth1.
Say that, like compute the Pauli operators.
So maybe let me put it this way.
What's the problem?
So yes, okay. So yes, so maybe here's this one. So I consider all the circuit that has this structure. Now my test is the following. Give me any circuit that looks like this. You output the poly-observable. What I'm saying is that if you can, the task of doing this for all possible choice of circuit with this structure is hard. So we call it a worst case result. So there's definitely some circuits in this class that are actually easy. For example, you just choose those Clifford operator to be identity, then the resulting stages factorizes, then they're easy. And there's an interesting question of what are the average case hardness? So can you identify some ensemble of circuit that looks like this and computing observable that could be easy or hard? Actually, we have some unpublished results here that's interesting as well. I can talk about it later.
So this n cube result for the Pauli observable, where can I find the proof on that?
Oh yeah, I'll explain proof later on. I'll explain the high. It's published, and I'll give a high level overview of how we prove it. Okay. Yeah, but again, error bar matters. For a quantum computer, you achieve additive error, and for the same error bar, we're able to give a classical algorithm, efficient classical algorithm, to accomplish the same task. So that means if you have a quantum circuit with one layer T gates, or any magic gates, any diagonal magic gates, you don't have any quantum advantage if your task is computing an amplitude or computing an observable. Now we know we have a classical algorithm that helps you sample like a logarithmic size marginal, but we still believe that sampling the whole distribution is hard. So if you have one layer T gates and your task is to literally sample the entire distribution, you still have quantum advantage so far. Okay, people looks happy, so I'll first give a hint of why you even expect some of the hard results, because I previously told you that if you have one layer Hadamard gate, you have one layer superposition, you don't generate interference. But that's actually not true in the poly basis, because if you look at your initial state, say 0, your initial state is already an exponential sum of poly operator. So let me write down this 0, 0 as a density matrix. I told you it's generated by the Z1 and Z2. And if you have n generators, you have 2 to the n elements because it's like Z2. So you have 4 operators here. And now after you evolve it through the first layer Kiffer, you get some other operator. But once you go through the magic gate, these are Hadamard. So you're already passing an exponential sum through like one layer beam splitter. That's actually already enough to create interference. That's why you see some of the hardness result. But turns out this interference is way more tractable than some more complicated ones. That's why if you allow the error bar to be a little bit bigger, like a reasonable error bar, then you can actually do classical simulation. Okay, so that's the intuition. Let me just jump into a high-level overview of how we show these results. So let me start with the hardness sampling and hardness of computing amplitudes. The main technical tool I'll use is this circuit. It's called the degree 3 IQP circuit. what it does is you start with a 0, you apply 1 layer header mart, and then you do a bunch of phase gates. You're allowed to do Z gate, which you apply a -1 phase when your input is 1. You're allowed to do CZ, it's a Clifford gate. Or what it does is you apply -1 when your input is 1, 1. And you apply 1, as you don't apply anything when its input is other computational basis. And lastly, there's a bad guy, CCZ. CCZ is not a Clifford gate, it's a magic gate. And it applies a -1 phase when the input is 1, 1, 1, and do nothing otherwise.
Sorry,
Yes.
I missed the question. Why you continuing this?
Yes, I will use just wait until next slide. I will show that this circuit secretly has T depth 1. Okay. Yeah. So basically, if you look at these are all diagonal phase, they all commute. But if you look at the phase pattern here, it's basically trying to implement some like a degree 3 polynomial function where for any improved computational base string, it gives you a phase. And computing amplitude in this circuit turns out it's just summing up this degree 3 polynomial. And let me just state the result directly. If you have a machine, if you have an algorithm that can compute this degree 3 IQP circuit for any size n, where m is polynomial in n, and it's the qubit we actually want to simulate, then you can compute any path integral. So basically, the hardness of computing this degree 3 IQP circuit encompasses the hardness computing any path integral. And the technical jargon is called GAP-P. It's a complexity class. Don't worry about it if you haven't heard about it. And the idea is that if you look at this function, this is a degree 3 polynomial function. You cannot express any function from this, but what you can do is you make a bigger g of x. So let's say you want to compute f of x and sum it up. This is a path integral. Very roughly, what you can do is you find a g of x that takes more input than f of x. So let's say f of x is like you input 10 bits, output 0 or plus or minus 1. Now you can cook up a g of x that inputs 20 bits. And somehow the structure of g of x encodes the information about f of x. And then by summing up g of x, you automatically get the answer for f of x. That's a very hand-wavy proof. If you're interested, I can show you exactly how it happens. And the test basically, now I'm going to show that this degree 3 IQP circuit is exactly a T-depth 1 circuit. So if you can simulate T-depth 1 circuit, compute this guy's amplitude, you can compute this amplitude, and therefore you can compute any amplitude. So that's why it's hard. Okay.
I'm missing something, but Adamars are Cliffords and the rest is Cliffords, right?
Yes, anything that's not Clifford is in purple.
So purple.
So the only non-Clifford gate here is the CCZ gate.
Yeah, so in purple, then you're saying that whatever is in purple is not Clifford?
Yes.
Oh.
And I'll show you that you can rewrite this circuit as this one, and moreover, every single diagonal element here is either T or T dagger.
Okay, that's the part I guess I was missing. So I was under the impression that any control Z gates would be Clifford.
Oh, actually, that's not true. Only control Z is Clifford. Now, if you have multiple control, they become they are not Clifford gates.
Hopefully.
Yeah, Toffoli is like CCZ, and you sandwich Hadamard, and they're not Clifford. Okay, yeah. So I'll show this reduction. I'll show you that you can compile a degree 3 IQP circuit into a circuit with 1 layer T gate. And also we know there's some more complicated arguments showing that sampling this degree 3 IQP circuit is also hard. And therefore, if you can sample this circuit, you can sample degree 3 IQP, which is hard. Okay, and I will really just flash through the proof. Actually, okay, here it is. I will flash through the proof. You can read about the detail in the paper. The first thing we're gonna do is we'll try to put the Z gate, CZ gate, and CCZ gate into 1 layer. So previously, now at least pictorially, they look like they're in different layers. So I'm gonna try to put them in 1 layer. The trick is that Z gate, CZ gate, and CCZ gate, they are all diagonal gates. So they're just applying phase in a computational basis. And there's a parallelization trick where you introduce ancilla, like additional qubits. So what I'm going to do is I'm going to introduce ancilla in blue. They are initialized in 0. I'm going to do some C0 to couple the data qubit and ancilla qubit. And in the ancilla, I can put all the gate in parallel. After that, I'll undo some of the C0 so that I can disentangle my ancilla from the data qubit. So no matter what's the input, ancilla always returns 0. Okay, that's the first trick. And the second trick is I want to turn CCZ into T gate. So Z gate and CZ gates are Clifford. CCZ is not. So I'm going to show you how CCZ can be compiled into T gate in one layer. So first thing, CCZ gate has the following decomposition in T, T dagger, and C0. They're not in the same layer. But we exploit the fact that C0 gate has some special symmetry, namely their permutation in the computational basis, to squash it up, to squash it into one layer. So this circuit is equivalent to this circuit. Again, we have to introduce ancilla, and this ancilla will be decoupled from the data qubit after computation. So it always returns to 0, no matter what's the input. So together, so the proof goes by following. First thing, you put all the Z gate, CZ gate, CZ gate to one layer. Second thing, you handle CCZ, it's a bad guy. You show that it has one layer T gate. And therefore, degree 3 IQP circuit has one layer T gate. Is this clear? Okay. And then by hardness of degree 3 IQP, we can show that T-depth1 is hard. Okay. Now I'm going to talk about poly. Yes?
So now that this degree 3 circuit can be casted in the form of the diagonal.
Yes.
Magic gate. But shouldn't you also show that any depth1 circuit goes back to the...
No, yeah, good question. So again, this is a question of, so degree 3 IQP is one corner of all T-1 circuit. Not all T-1 circuit are degree 3 IQP. Well, I'm saying that this is a worst case result. So if you have the algorithm that simulate all the instances in this class, including this tiny corner, then you are able to solve some very hard problems.
Yeah. Show that the CQIQC is harder than...
This is like basically... Yes. Yes, so this is probably the hardest instance among all T-depth1. Good point. Thanks. Okay, if there's no further question, I'll proceed. Now let's talk about Pauli observables. So surprisingly, while I showed you that computing amplitudes is hard in T-depth1, computing Pauli observable is easy, and it's order n cubed classically. And the idea is that now we can exploit the special symmetry of T-gates. T-gates belongs to what's called the third level of Clifford hierarchy. So I'm not going to define where it is, but third level means that this gate, if you evolve Pauli operator with something from third level Clifford hierarchy, you turn it into a Clifford gate. So let's say I evolve X with T and T dagger. You turn it into X times S up to some global phase vector. And this is a Clifford operator. So S is a 45-degree rotation, X is a 90-degree rotation. Oh, sorry, S is a 90-degree rotation, X is a 180-degree rotation. Okay. So I'm going to exploit this fact that T-gate belongs to a third level Clifford hierarchy. So this is the circuit I'm using. I'm trying to compute this Pauli observable. I'm trying to evolve some state and with some magic gate, and I compute some Pauli observable. Now I will use the fact that if you have a Pauli operator and these are in the third level Clifford hierarchy, for example, T gates, you turn them into a Clifford operator. So I just make the substitution, plug it here. Now the task of computing Pauli observable becomes a task of computing an amplitude in a Clifford circuit. And we know Clifford circuit can be classically simulated. That's why computing Pauli observable is easy. Okay, this is probably the easy part.
It's a very particular specific construction where you have given and for Western Poly and then leave it that way. Or you can always bring any circuit to this form. Like,
Yeah, so for any T-depth1 circuit, you can always bring it to this form. I'm just using the fact that all the T gates or all the gates in the third level Clifford hierarchy, they're in the same layer. Okay. But this property requires me to exploit a special symmetry, third level Clifford hierarchy. Turns out if you break this symmetry, then this property fails. So what I'm going to do is, I'll replace T gates with a square of T, so it's even a smaller angle rotation. Previously 45 degrees, now it's 22 degrees. Or I can add one more layer T gate. If I do either one of the two, then the hardness of computing polyobservable becomes gappy complete again, which is the hardest computing any path integral. So it's hard. And the idea is that I will choose a gadget called Hadamard test. It's a very standard trick in quantum computing. And this Hadamard test turns computing amplitude into computing polyobservable. So the circuit looks like this. I have some state, psi. I have a unitary, U. Now I'm going to introduce one more ancilla, initialize to 0, and then I do a Hadamard. I do a control U. I do Hadamard again. Now if I measure the Z operator here on this ancilla, the Z operator corresponds exactly to this amplitude, or the real value of this amplitude. The trick we'll use to turn degree 3 IQP circuit into a Hadamard test. So I grab this circuit. This is a unitary. I'm gonna just take H into absorb it into 0, so turn it into plus state, and then I'll call this guy my U. So your Hadamard test looks like this. I have some plus here. I have this is ancilla, and now everything here, if it was control Z, it becomes control Z. If it's like control Z, it becomes you control 3 times and Z. So it's like you add one more control to every single gate. Now you have, again, these are diagonal gates, so you can parallelize them. But tricky things now is that you have CZ gate, you have CCZ, which is not Clifford, but in the third level of Clifford hierarchy. Moreover, you have CCCZ. You have 3 control, 1 target. This is not in the third level Clifford hierarchy. In fact, it's in the 4th level Clifford hierarchy by, that's probably an easy guess, but it doesn't have the symmetry. It doesn't have the previous symmetry that you evolve a poly operator with 3CCZ, you don't end up in a Clifford operator. Okay. So, and the remaining task is show that, okay, so if I can compute the poly operator of this circuit, I can compute the amplitude of this guy. That means it's hard. So the remaining task is to show that this circuit, which contains some gates from the 4th level Clifford hierarchy, can be compiled to either 1 layer of square of T or 2 layers T. So it's very similar to before. I tried to do the compilation. And I'm not going to explain in detail. We did that. Looks like this. It's complicated. If you want to learn about it, you can read the paper. Yeah, there's actually some very interesting interplay between something called Clifford hierarchy and complexity transitions, which we discussed a little bit. But in the interest of time, I'll skip them. Okay, but is this clear? How we show that once you replace T with square of T, or replace T with 2 layers of T, then it becomes hard. There are these hard instances that if you can simulate, you can compute any path integral. Okay, great. This is doing great. Okay. Now I'm going to explain the classical algorithm for this. I just previously for when you relax the error bar. Previously, I told you that these results, all the previous hardness result, they are either exact result, so you have to compute these values exactly, or you allow the error bar to be like 10% off. I also told you that 10% off is not a realistic error bar. The realistic error bar is like 0.01 off. The error bar should not scale with your ground truth. And if you do not allow your error bar to scale with your ground truth, we're able to give an efficient classical algorithm to compute amplitude and polyobservables. And that means that you rule out the quantum advantage in estimating observables if your circuit has only one layer of T gate. Yeah, by the way, I should also emphasize that this algorithm applies to any diagonal magic gate 1. So it can be T, it can be square root of T. In fact, this gate can be non-local. I can have a non-local diagonal gate. All I need is a query access to this element. So give me an entry, I know this element. That's all I need. I will quickly explain how we do this. So basically, we'll use the following trick. So I start with 0, I evolve with Clifford, I get a stabilizer state. I'm going to call it a psi stabilizer. So these are guys that are ground state of some commuting Pauli operators. I'm going to squash it out. And next thing, I'm going to use a trick to push all the diagonal gates to the right-hand side. They turn into some different diagonal gate. Don't worry, I'm not going to explain in exact detail. But after doing this, you get a stabilizer, a Pauli operator, a diagonal gate, some different diagonal gate, stabilizer. If you're not familiar with this diagram, this is the expression. And since this is a diagonal gate, these are all diagonal gates. So I'll explicitly write it down in the computational basis. I'll sum it up in the computational basis, where on the right-hand side, this is the diagonal elements. I don't sum over the off-diagonal elements because they're all 0. And on the left-hand side, it's a density matrix times the operator on the right-hand side. So this really looks like a sampling problem. It looks like I'm sampling some operator from this distribution, except this is not a distribution. So this is an operator stabilizer, some density matrix times the Pauli operator on the right. This is not even a Hermitian matrix. It's really weird. But what we're able to show is that if you only focus on the diagonal elements, turns out they are either all 0, which means your opposite excitation value is totally 0, or is some mixed stabilizer state. So basically something you can classically sample from. And then on top of that, there are some phase, but you know what they are. So we turn this problem into a sampling problem where we sample the diagonal elements, which is actually classically easy. You use like stabilizer simulation to do that. And then you sample and evaluate the excitation value of this diagonal operator. Yeah, this is a really quick flash through. We have a studio algorithm written in the paper. So if you're interested in the detail, please check it out. And lastly, I'll just mention that computing amplitudes, this is the task computing Pauli observable. For computing amplitudes, you just sample the stabilizer operator of the amplitude one compute. So 0, 0 is sum over all the z operators. So you just sample all these z operator, and for each z operator, you do the sampling. So it's like doing Monte Carlo. You sample then jointly. Okay. So that's the part of the algorithm. In the last maybe 5 or 10 minutes, I will answer the previous question, which is why magic depths, if you look at just one circuit, it's actually not a robust quantity. Turns out you can reduce the magic depths in certain cases. And this is not done by us. This is done by some subsystem work we're scooped. But it's very interesting, so I'll talk about it. So let's consider this kind of circuit. Have some Clifford unitary, one layer T gate, Clifford unitary, one layer T gate, and so on. Naively, you look at this one, you will think that this guy has a very large magic depths because each T gate is put in different layers. But unitary is a very big object. It tells you for how you rotate from one exponentially large space to another exponentially large space. But you do not really probe a unitary on a quantum computer. What you always see is this action on a state. So let's say you start with 0 and you rotate U with 0. So you don't see most of the information unitary. You only see its action on a subset. And just to be more clear, you can have 2 different unitaries, U1 and U2. They're different. They're not the same operator, but their action on the states are the same. So that they have the same first row, but subsequent rows are different. First columns, whatever. And now, maybe U1 have a very large mesh depth like this guy, but U2 may not be. So this one state I prepare using large magic depths, but it doesn't rule out the fact that I can prepare the same state using a different unitary, which has a smaller magic depth. And that's actually good for us because we know that if you have a small magic depth, it's a structure you can exploit in classical simulation. So let me show you some example. So I'm going to set C to be like random Clifford gates. So you randomly choose one instance from the ensemble of all Clifford gates. And it's first observed numerically that if you have a random Clifford T gate, random Clifford T gate, and so on, and you apply it to 0, you apply it to a stabilizer state, you can generate exactly the same state using a different Clifford operator and one layer T gate. And you can do this with high probability for up to n minus one layer T gates. So basically you can pack almost n layer or n T gates. You can fully pack this first layer. Of course, you cannot pack more than n T gates in one layer because you only have n qubits. But this is basically saturated. Yes, question? Okay, so for this one, this C has to be you have to choose it randomly from the full Clifford group. It's a typical, it's a probability argument. And the number of T gates, you can keep doing that up to n layers, n minus order 1. So it's actually quite surprising. You would think that, you use like a big Clifford operator, it's highly scrambling. You scramble this operator, make it very non-local, and then use T gate to interfere. But turns out it's actually not true. Turns out this scrambling actually prevents you from generating interference in the polybases, which is at least something I didn't see before. It's very interesting. And in the last slide, I'll explain. So let me just put it this way. 3 months later, some other group pulled out an algorithm. This algorithm helps you for just input a circuit with Clifford gate and T gate. They're able to just push the T gate to your first layer. If your circuit looks nice enough, you cannot do this for all T gate, all circuit, but for some circuit, such as this random Clifford plus T circuit I showed you in the previous slide, this algorithm works. They show you how to push it to your first layer. Let me point out that this is like actually this just happens a few months ago. There's a lot of open space for understanding what's going on here as well. Lots of opportunities. And okay, I'll conclude. I just told you the story of how the distribution of T gates, the fact that they concentrate in one layer can help with classical simulation. And one immediate question is, can you find out more examples of magic depth 1 circuits and exploit the fact that they have this structure to do classical simulation? It's something that immediately brings you some benefits now because you can just literally run this algorithm on classical computer. You don't need a quantum computer to simulate this kind of circuits. And in particular, can we come up with like different ways to do this magic depth reduction? Maybe push gates that are like non-local gates. So far, that previous algorithm only works for local gates. Or can you not push that in the first layer, but push it somewhere in the middle? And we know that if you can push T gates in the middle, it gives you more power. So there are states you can express by using one layer T gate in the middle, but you cannot express that in the first layer. So the position of the T layer actually matters. And also, I showed you that sampling one layer magic gates can already give you quantum advantage. So can this be used for, like, for example, near-term fault tolerance experiments, where you have a limited number of T gates, so you cannot like synthesize like complicated Shor's algorithm. But rather than doing so, can you just put T gates in, like, let's say, final layer and do some sampling tests here, and you already have hardness. And moreover, you know that computing observable can be done classically, so you can use while sampling from a distribution is hard. Once you get the sample, you can compute the observable classically and verify your sampling. Now, it's not going to be like a full verification. It's only a partial verification. You check something observable, but it gives you more confidence in doing this kind of experiments. And lastly, I think this is the most interesting realm, which is, I do believe that we should really think of quantum algorithm as doing interference in polybases. We know that quantum computer is powerful because we use path integrals to like sum up amplitudes, and somehow the right answer that encodes some hard problems have a constructing interference. So and for fault-tolerant quantum computing, the most natural basis is a Pauli basis, because that's where we use magic gates to generate superposition, maybe generate interference. And whereas all the previous quantum algorithms, like Schur's algorithm, they think about interference in the computational basis. It's definitely easier to think about our algorithm in a computational basis. It makes the math a lot cleaner, but it's not natural, because now in real life, when we do fault tolerance, we do interference in a Pauli basis. So the big question now is, can you think about quantum algorithm from this T-depth perspective, think about interference in Pauli? Maybe if you add one more layer T-gate, you can already create something that's useful and classically hard. Okay, with that, I will conclude, and thank you very much for your attention.